We said that a z-score is a transformation of your original data set. Now, the first transformation was subtracting the mean from each and every one of the data points in the original data set. We covered that already with the shift in our data. Now we're going to scale our new data set. That's the second transformation. To create a z-score, the way you scale your new data set is to take the new value, the new column is going to be the column of deviations, all the values that you created in the first transformation, divided by the standard deviation. If we're working with a population, then we'll use the symbol sigma, the population standard deviation. If we're working with a sample, we'll use the symbol S, the sample standard deviation. Let's see how this plays out in practice. Great, we saw in the last video in D2 that the mean shifted data was 0, and this would always be the case for a standardized data set. Notice, however, that our new data column, D, has the same standard deviation as our original data column, B. And that's because we haven't scaled it. So in order to standardize your data, what you do, remember, a transformation of a transformation. We're going to start with column D, and we're going to divide each and every data point in D by the standard deviation. Take your pick, whether you want to think of it as the standard deviation of column B, the original data set, or whether you want to think of it as the standard deviation of column D itself, the transformed data set. They're always going to be one and the same. All right, let's do that. We're going to head on over here, say equals D6 divided by, and we'll just go with this standard deviation. It's all one and the same, D3, and I want to lock in that value, so D3. As such, Google Sheets says, do you want me to fill all the way down? We are now looking at a column of z-scores. What does it mean to be working with z-scores? Well, by definition, you have a standardized data set. Each and every one of those values in our new data column, a transformation of a transformation, combine in such a way that the mean will be 0 of this new data set and the standard deviation of this new data set will be 1. And what's really fascinating here is that how you can go about interpreting this now. Every single one of these individual values are what we would call z-scores. So in our original data set, we had just like a value 35.33. Well, what this new column tells us, this new z-score, is that 35.33 rests 0.66 standard deviations above the mean of your data series. In the next data value, we had 18.88, and what this is telling us is a z-score of negative 0.52. The negative is telling us that 18.88 lives 0.52 standard deviations below the mean. So positive z-scores tell us that our original data lived above the mean. Negative z-scores tell us that our original data value lived below the mean. And really importantly, it's telling us how many standard deviations above or below the mean that each data point in our series works. So a lot of times we can just look at our data series as a whole as standardized series, which is what I've done. It's not uncommon at all to single out one particular data value. This happens all the time in, say, inferential statistics, and we're thinking about the z-score associated with that one particular data value. So my data value was 47.4, and the corresponding z-score is 1.538. That's how you take a z-score. What's going on? What does this look like? And now we've got our data centered on 0, and instead of reporting like negative 25 to 25, the way that we saw our previous column operated, now everything operates, in this case, between negative 2 and 2. It's telling us the number of standard deviations below or above the mean that each individual data point lives. All right, Lines on Clay users, you know the drill. You're going to head over to File, create a copy using the link that we gave you, and follow these instructions, and you will, from scratch, create your own set of z-scores. Enjoy.